Hello everyone, this is Ahmad Marei. My colleagues are Rashad Kilani, Hassan Ahmad, Muhammad Jamal, and Emmanuel. In today's presentation, I will be delivering a brief about our research titled Evolutionary-Based Production of Bearing Capacity of Shallow Footing based on Soil Classification of Sandy Materials. To start with, the allowable bearing capacity of foundation is the maximum gross stress intensity to which the soil at the base of foundation can be subjected without risk of shear failure and excessive settlement. As everybody knows, several parameters should be considered while deciding the bearing limit of the sand, including the unit weight, internal friction angle, and foundation size and depth. The purpose of this research is to find out a correlation between the soil classification of sandy materials and the angle of friction. To do that, we have used a relatively new program titled Evolutionary Polynomial Regression. It is a data-driven method based on a recent evolutionary computing technique designed to search for polynomial structures representing a system. The EPR consists of two stages. The first stage is to identify the main structure using genetic algorithm, and the second stage is to estimate the parameters using least square regression. The EPR combines the best features of conventional regression with symbolic regression and with genetic programming. Previously, EPR has been utilized in several geotechnical applications, including prediction of earthquake-induced soil liquefaction, modeling permeability of soil, and settlement estimation of shallow foundations. The first step was to collect the data, and we have collected a total of 976 direct shear test results distributed among 5 soil classifications of sandy material as listed in table 1. The soil classification are SM, SP, SPSM, SW, and SWSM. After that, we identified the model inputs and outputs. The model inputs are fine content, percentage of fine content, and SPT and value. The model output was the angle of friction. The available data are divided into a training set to generate the model and a testing set to examine the performance of the model. This is basically a machine learning program. The training set represents 80% of the whole data, whereas the testing set represents 20% of the data. The two sets have been chosen in a way that they have the same statistical population by making the statistical parameters for both sets close to each other. The main reason for performing a statistical analysis is to achieve a robust representation of the whole population of both sets. The statistical parameters are the maximum values, minimum values, mean values, and the standard deviation. The parameters used to develop the EPR models are listed in table 3. The regression type is statistical. There is no function. The term is from 1 to 5. The range of exponents is 0, 0.5, and 2. The generation is 10. And the constant estimation method is least square. After that, we were able to run the EPR and get the following 5 EPR models. Each model represents a soil classification, as you can see in this slide. So what we have done after that, we have used these EPR models to come up with a table that can be used to predict the net allowable bearing capacity. Once we have the soil type, the SM, the foundation size, and the density of the soil based on the SPT value, we can predict the net allowable bearing capacity. And we have done that for the 5 soil classifications of sandy material: the SM, SPSM, SP, SWSM, and SWSM. Generating this table had followed with some assumptions, including the hammer efficiency is 60%, the footing depth is 1 meter, the unit weight equation is as per ASCE 1996. We use the Terzaghi equation to estimate the shear. We use the elastic method to estimate the settlement. The modulus of elasticity equations were as per Pigman. We assume that the site is dry and there is no water effect, and a few other assumptions that can be found in detail in the paper. So basically, after obtaining the EPR models, I'm coming up with a predicted net allowable bearing capacity table. We had to measure the accuracy of these models, and it happened to be accurate. So here we do have these two graphs. The left graph represents the statistical analysis of the SM material. The coefficient of determination of SM is 89%. The root square mean error is 1.1 degree, and the mean absolute error is 1.5 degree. The coefficient of determination of SPSM is 87%. Coefficient of determination of SP material is 87%. Coefficient of determination of SW material is 88%. And the coefficient of determination of SWSM is 87%. Based on these graphs, coefficient of determination, root square mean error, and the mean absolute error, it can be concluded that the models are accurate and they are solid. After that, we have conducted the parametric study to verify the response and remoteness of the EPR ideal models. The parametric study is capable to confirm whether the response of the EPR model matches the conventional methods or not. The study has been concluded by increasing the SPTN values to measure their influence on the angle of friction. The study confirms that EPR model can capture the underlying physical meaning of the friction angle. So basically, once we increase the angle or the SPTN value, the angle of friction increases as well. In conclusion, statistical analysis confirms the accuracy of the EPR ideal models. The coefficient of determination ranges between 87% and 89%. The parametric study confirms the ability of the EPR models to capture the friction angle physical meaning. In conclusion, the EPR model can predict the friction angle based on the sandy material classifications. Therefore, the EPR ideal models can be used in geotechnical applications within the parametric ranges listed in Table 2. A special thanks to Arab Center for Engineering Studies, ACES, for providing the direct shear results and supporting us during the research. So many thanks to ACES for supporting us during this research. And by this, I conclude our presentation. I would like to thank you for your time, and I hope you have found it to be useful. Thank you again, and have a productive day. Thank you very much.